Welcome to the afternoon session. First up today, the three contributed talks is Edoardo Airoldi, talking about the exchangeable graph model for statistical network analysis.
Hi everybody. I want to thank the organizer for giving me the opportunity to present my work here. This is a perfect audience for this talk, and I look forward to feedback, email, stop me after the talk, and so on and so forth. Today I'm going to talk about the exchangeable graph model, and so to set the context for this talk, I'm going to describe statistical element of graph data analysis. So my data actually looks like a graph or a collection of paired measurements. So measurements of pairs of objects. You can imagine proteins, and so an interaction, a physical binding event between two proteins would be a measurement. And today I'm going to describe the binary case, so you can imagine this collection of measurements to be displayed like a graph, G, and N is going to be the set of nodes or proteins, and Y is going to be the adjacency matrix, a binary square adjacency matrix. So more in general, when you have measurements on pairs of objects, you will have square matrices, possibly more than one if you repeat the collection of measurements on the same N nodes. And so in this talk, I'm going to describe a model that looks at the graph and try to resolve the connectivity pattern that you see in the graph in terms of node-specific binary strings. And I do that using a likelihood and some exchangeability assumptions. The second part of the talk is going to be more work in progress, so again, feedback is very much appreciated. Instead of compressing a 45-minute talk in 15 minutes, I thought I'm going to describe some background so you can appreciate where the model comes from and what's the context, the methodological context for the model. Then I'm going to describe briefly the model and a couple of results that you can derive using this model, and then I'm going to talk about applications. There's two particular applications that sort of drove me to derive this model. So the background consists of other statistical approaches to analyze measurements of collections on collections of measurements on pairs of objects. So for example, this class of model is called the P-star, or the exponential random graph family of models, and the probability of the whole graph or the whole collection of measurements is going to be described by an exponential family where these sufficient statistics are statistics computed on the whole observed graph. And for example, different people in different communities have chosen to pre-specify certain statistics that they think they are interesting for their application. And so the simplest statistics is obviously the number of edges in the graph, and other statistics that have been heavily used in the applications to social and biological sciences are, for example, the number of triangles. And the possibility to represent or to write down the likelihood is due to an initial factorization that's been derived by Frank and Strauss in 1996. Snyder et al. Have a more recent publication on this topic where they describe a number of different statistics and the application that they are useful for, and then an extension of this model to the dynamic setting where you have a temporal collection of graphs has recently been developed by Haneke and Xing. A second class of model, more recent, is called the latent space models. And some of the ideas in this class of model I'm going to leverage for my own purposes. And so the idea here is that, again, you have your collection of binary measurements, the edges, and the probability or the log odds actually to observe an edge will depend on some features of some node-specific features that correspond to the two nodes that are involved in that edge. And in particular, these two features in this class of models live in a lower dimensional Euclidean space. And so in the paper, for example, or in the literature, there's a way of choosing an optimal, in some sense, dimensionality for the latent space. But the idea is that if points are closed in this latent space where you project the graph node by node, then if two nodes are closed in the latent space, then the log odds of an edge between these two nodes is high. And the original publication is Hoff et al. In JASA 2002. Again, there's in the computer science literature, a dynamic extension appeared in NIPS by Sarkar and Moore. And then there's a very nice paper in JRSS with discussion by Hancock et al., Hancock, Raftery, and Tantrum, where basically they try to put some cluster structure in this latent space. A third set of statistical approaches to graph data is consists of the block models. So in block models, the fundamental idea is that you try to identify sets of nodes that behave, that connect to other sets of nodes in a similar way. And so technically, there's sort of two sets of parameters that you're interested in. First, a permutation or a subset of a collection of sets of nodes, which I will call blocks, or people in the literature actually refer to as blocks, and then a mapping between nodes to blocks. So you can imagine a mapping between nodes and blocks. So in order to instantiate that, you can sample node-specific vectors from the Dirichlet distributions, and the Dirichlet vector of node I will carry information about the degree to which this node I belongs to the different blocks. And then there's another set of parameters, the block model itself, which if, for example, this Dirichlet distribution consists of k-dimensional vectors, in the model you will have k blocks, and this B parameter is actually a k by k matrix, and each entry in the matrix is a Bernoulli parameter that tells you the probability the two nodes in the two blocks will actually connect. So to fully instantiate the likelihood, you sample for every node the mixed membership vector or these node-specific latent variables. And then in order to build an edge between node I and node j, you just take the inner product between the mixed membership vector of node I and node j weighted by this block model. And the original idea of structural equivalence that informs the block model is due to Lorraine and White in the Journal of Mathematical Sociology. Nowicki and Snyders have developed some NCMC and some generalization of this model. And then myself with colleagues have developed a variational inference scheme for this model and another level of generalization to be able to tackle large graphs. Because one of the main, I would say, pitfalls of all these models is that MCMC that's been developed scales up to maybe 100, 150 nodes. And if you look at all the papers in JASA, for example, all the examples or the applications, they can't go beyond a certain amount of nodes. So some remarks. Well, the exponential family of random graphs summarizes the graph using the exponential model. On motif counts, you have to pre-specify the motif. One of the main problems or one of the main shortcomings of this model is that it's impossible to do node-specific predictions because there's no node-specific parameters. In the latent space model, again, you project the graph on a lower dimensional space. You do have node-specific parameters, so you can do node-specific predictions, but there's a hard identifiability problem because every rotation of this latent space leads to an equivalently maximally likely solution, and there is no clustering effect. And the mixed membership model sort of map nodes to blocks with similar connectivity, and the projections from nodes to the block model is fractional using this mixed membership, this Dirichlet latent variables, and it's sparse. Well, the degree of sparsity is actually inferred from the data, but you could, if you wanted, enforce sparsity by fixing the hyperparameter of the Dirichlet distribution. But it's complicated in a sense. It's complicated because there's these two sources of variability, the block model on one hand and the mixed membership map on the other end, and they compete to explain the variability in the connectivity patterns of the graph. Although not quite, because the block model tries to explain variability that it's global and asymmetric, whereas the mixed membership map tries to explain variability that it's local to a node and symmetric. So we are not introducing in a block model an additional identifiability problem, but it's still a little bit too complicated. And so I guess my goal in trying to extend or to summarize this model for the specific problem that I will discuss in a little bit was to try to find a tractable model, so a simpler model, but that sort of shares some of the characteristics that make sense from my application of these models. And one is that of having node-specific attributes, so to resolve the complexity of this graph into node-specific attributes, and then that of sparsity. So these attributes also need to be sparse. Now I'm going to describe the model just briefly. So the exchangeable graph model is very simple. You sample binary string for a uniform distribution on the vertex set of the hypercube, for one binary string for every node, and then so this is sort of reminiscent of the idea in the latent space model. And then you sample an edge using a function q of the two corresponding bit strings for all pairs. And again, bi is a binary string and it's k bit long. And one way of thinking about this exchangeable graph model is just a step up in complexity from the classical Erdős, Renyi, Gilbert model. So there's a number of specifications that, depending on the application, one may want to consider. There's some regularities or some general remarks, though, that should hold. So in order for the model to summarize the data, the number of bits in every string has to be less than the number of nodes itself. Otherwise, you have more than n square latent variables to summarize n square data points. This function is asymmetric in the argument, and the reason for it to be asymmetric is because in my applications I have directed graphs, and so I have to summarize a non-symmetric adjacency matrix. But you can extend, or you can find a Q function that works for your data. And then I guess the problem, the interesting challenge, is how to control the sparsity of the bit strings. And so the idea, it's very simple, is to imagine a three-dimensional hypercube and think of a Dirichlet distribution and how it works on the simplex. And so the idea is to extend the type of density that the Dirichlet sort of induces on the simplex in the hypercube. So the idea is to concentrate the density in the corners of the hypercube. And so you can imagine sampling point in the hypercube hi, k-dimensional, and then sample IID bits using the components of this hi vector as Bernoulli parameters. And so we will write this distribution that I'm not going to describe any further as the bit distribution on a bit string of length k. Depends on a parameter alpha that goes between 0 and infinity, and you can imagine this parameter alpha works as the hyperparameter of the Dirichlet distribution, as the parameter of the Dirichlet distribution. As it goes to 0, the density gets concentrated in the corner of the hypercube. And so the bit strings tend to be sparser and sparser. So what kind of results can we sort of derive for this model? Well, one classical result that in the Erdős-Renyi random graph model people have derived over and over is the emergence of the giant component. and the proof in that case depends on some properties of the tail of a binomial distribution. Here you can represent the probability of an edge. You can look at the probability of an edge from sort of two perspectives. The probability of an edge decreases with k, so in more complex model, the chance that an edge happens at random is lower. And on the other end, the probability of an edge increases as with the inverse of the parameter of the distribution. And the idea is that the concentration of a density, the more concentrated the density is in the corner of the hypercube, the higher are the chances of observing an edge at random. And so we can observe, again in this model, the emergence of a giant component, and we can map the phase diagram now in 2 dimensions. And we can find the phase transition, but there's structure in the giant component that there isn't in the typical Erdős-Renyi random graph model. And so here is just an example for bit strings of length 5. And so what I'm showing here is a sample of a fully connected graph. And you can see that so the way to prove actually the emergence of a giant component, you have to use a different strategy. You look at branching processes from every node, and then you only have n edges. And so if the conditions are good for this branching process to grow indefinitely, on n nodes they have to intersect, and then you can compute the size of the intersection, and you see that it's of a certain size. And so anyway, you see that you have these 5 giant clusters, and then as soon as interstitial nodes, nodes that sort of belong to 2 clusters appear, the graph suddenly becomes fully connected, and you don't need a lot of them. That's the key. And so here I'm showing, for example, as the value of alpha decreases, so as I'm concentrating more and more the probability on the corners of the hypercube, for a fixed k, the clustering coefficient increases over and over. This is just a way of measuring what happens for a fixed k as alpha as we concentrate the density. Okay, so how to do inference on these bit strings? Bit strings are actually latent variables in this model. So, well, now the bit strings come from this distribution. For all the edges are sampled according to Bernoulli, where the probability Q is a function of the 2 corresponding big strings. You can write down the likelihood. You have to integrate out the latent variables. It's hard. We do, instead of doing EM algorithm, we have to do an approximate EM algorithm, where the step is basically approximate. So now I'm just going to describe a couple of applications, because the reason why I worked on this model in the first place is not to just play with graph connectivity. I had a couple of problems in mind. And so the idea was, if I have a model that steps up in complexity with respect to the Erdős-Renyi random graph, well, I want to be able, or I want to expect this model to sort of help me to solve some problems that I have. So one set of practical issues arises in genomics. So you can imagine protein interactions. The way proteins carry out function in a cell is by grouping together into what biologists call stable protein complexes, and there's plenty of empirical evidence for this. The idea is that when you take measurements, a protein may belongs fully to one complex. And so the idea of mixed membership for this specific application is not really appropriate. You should have an idea for, you should implement an idea of multiple membership. So actually this distribution on the unit hypercube itself helps us specify multiple membership, and it's useful on its own. And then there's a number of cases where you're interested in understanding or in finding sort of protein complexes of a certain size, or computing the p-value. How surprising is a protein complex of a certain size or is a specific protein complex. And the standard in the community today is just counting edges and thresholding. And though this is a very simple model-based approach to compute the probability and to induce a distribution and to decide in a statistically principled way where you should do the thresholding, for example. And then also in functional genomics, when you're trying to understand the function of a protein, and here via homology, by looking at, for example, how proteins with similar sequence behave, again, in the biology community, the standard is to build graphs where genes with similar sequence are sort of connected, and then again, the game is to count edges, count overlap of neighborhoods and threshold, and so this model is helpful to bring some statistical considerations to the table. And then there's the second set of problems, which is more methodological, which is assessing the goodness of fit of statistical models of networks. And we really don't know how to do that just yet because the models are very different. The uses of the model are very different. And so one solution that this model offers is to sort of give you a handle on how complex your graph is by, for example, looking at how many bits you need to explain the connectivity in a certain graph, given a simple function q. Or you can actually look at the sample of graphs that you can sample after you have maximum likelihood estimates of your parameters, and so try to understand the model complexity in that sense. You can do model comparison, because now for every model, you can do model comparison. For every model, you can generate this sample of graphs, and then you can sort of infer the bit strings for all these graphs, and you can plot the information in these bit strings in a histogram. And now this is a very model-free way to compare graphs, for example. And you can do model selection. If you, for example, have a specific application and you have a target or an optimality criterion to decide what's the information profile that the model that you are fitting should have, you can use the bit string that you infer from the sample generated from your model to decide which model is best. And so just to conclude, in theory, this model should give you a new tool to explore the variability of the connectivity patterns in a graph. And in practice, it provides a likelihood-based approach to evaluate size of neighborhoods, and an information-based approach to measure goodness of fit in models of graphs. Thank you.
Time for maybe one very short question. Yeah, Subin.
So I wanted to understand a little better the bit k alpha distribution. So is this a form of beta Bernoulli distribution where you have a parameter on the beta and you have a hyperparameter alpha?
It's actually simpler than that. It takes from Aichi's work. So you have a multivariate normal, and you specify a covariance structure that depends on one parameter alpha and tries to match the dependence that you see in the Dirichlet, and then you project the coordinate by coordinate with the logistic function.
I see. Because if it was a form of beta Bernoulli distribution, which I guess it isn't, then you could infer the hyperparameter in very simple ways, and it would be actually very closely related to this sort of Indian buffet process.
The reason why I didn't do that is because I didn't know how to, to model the dependence between the bits directly. But maybe we can talk about that.
Okay, it's interesting. Yeah, very interesting.
Okay, let's thank Edo again.